In this video, we continue looking at functions involving logarithms from 5.1. We have a different problem statement here. I still might compute f prime and f double prime to get a better sense of the concavity of this function. But we're asked to compute f prime and find the equation of the tangent line at x naught and graph f and its tangent line on the same graph. I believe the version of this we have in the textbook specifies what x naught should be, but I wanted to leave this open to any value x naught in the domain so that we could change the value of x naught using sliders on Desmos.com and see how that tangent line changes at different values of x naught in the domain. So the first thing I always want to do anytime we've got a function that we're interested in is find the domain of that function. And remember, we cannot divide by 0, we can't take even roots of negative numbers, and we can't take logarithms of negative numbers or 0 in the real number system. So the domain of f is all real numbers x such that, well, we look for division by 0. Well, there's no division except for dividing by 2, so that's never 0, so we don't have to worry about that. Then we look for even roots, square roots, fourth roots, sixth roots. We don't have any, so we don't have to worry about that. And then we look at logarithms. Well, we say we do have a logarithm, and whatever's inside the logarithm has to be positive. Well, x plus 2 divided by 2 is positive when the numerator is positive. So the domain is a set of all real numbers x such that x plus 2 is positive, which just means that x plus 2, or x is greater than negative 2, or in interval notation, our domain, is negative 2 to positive infinity. So we know that the graph of f has an asymptote at x equals negative 2, because we know that the natural log of x will approach negative infinity. We know y equals natural log of x looks like this, right? As we approach x from the right, the function value goes to negative infinity. So as x plus 2 approaches 0, that's when x approaches negative 2 from the right. Then our logarithm here is going to go to negative infinity. And then we multiply by negative 1, so this is going to go to positive infinity. So we're going to have some number that's going to positive infinity, now minus a number going to positive infinity plus 4. So I'm not really sure if the function is going to go to positive infinity or negative infinity. I guess it just it depends on which one wins in the war, where this one goes to positive infinity and that one goes to negative infinity. But we would expect a vertical asymptote at x equals negative 2 if the function does go to infinity there. Actually, I know that as x approaches negative 2, this is going to be negative 2 squared, so we're going to have 4. 4 minus 4 is 0. So this part of it will go to 0, and then this part will go to negative infinity times negative 1, so it should go to positive infinity there. And so I'm expecting the graph or the function to look like that. Okay, so that's what I know so far, my domain, and then I've got that asymptote, and that the domain starts at negative 2 and goes to infinity. So the graph is going to be over here somewhere. And if we substitute 0 for x, we get 4 minus natural log of 1, because 2 divided by 2 is 1. Natural log of 1 is 0, because e to the 0 is 1. So we should get 4 when x equals 0. Okay. Let's see. Now let's compute the derivative now. See what happens. Well, the derivative of this function is the derivative of 4 minus x squared minus natural log of the quantity x plus 2 divided by 2. Derivative of 4 is 0. The derivative of x squared is negative 2x. Then we're subtracting the derivative of log of a function. So we've got 1 divided by the inside function, which in this case is x plus 2 divided by 2. And then we multiply by the derivative of the inside by the chain rule. Now dividing by 2 is the same as multiplying by 1/2. So that's 1/2 times the quantity x plus 2. And the derivative of 1/2 times the quantity x plus 2 is just 1/2. So what we get is negative 2 minus 1 divided by x plus 2 divided by 2 times 1 over 2. And if we multiply straight across, this 2 and that 2 reduce. And we just end up with negative 2x minus 1 divided by x plus 2. If we want, we can get a common denominator. Sorry about the weird glare again. Thinking of that as itself over 1. The common denominator of 1 and x plus 2 is just x plus 2. So we're going to multiply this expression by x plus 2 in the denominator and the same thing in the numerator, so that we're just multiplying by a well-chosen 1. When we distribute, we have negative 2x times x is negative 2x squared, and then negative 2 times positive 2 is negative 4x. And then we subtract 1, and then all of that is divided by x plus 2. So that's f prime. This is also f prime. If we look at this version of f prime, we see that as x goes to positive infinity, this part goes to 0, and the graph, or the derivative graph, approaches negative 2x. So this function f prime has a slant asymptote, y equals negative 2x, so it would pass through the origin, and then have a slope of negative 2. So we'd go down 2 and over 1 to get another point on the graph. And f prime is going to be slightly less than that as x goes to infinity. So it's going to be just below this line. The y values will be below it, because that is going to be a tiny positive number when as x goes to infinity. We're subtracting a tiny positive number, so we'll be below the line. Okay. Now, if we want to see where the derivative is 0, we could set this form of the derivative equal to 0 and solve for x, or we could set this form of the derivative equal to 0 and solve for x. Either one is fine. F prime is 0 when, let's take that numerator and set it to equal to 0. We have negative 1 times 2x squared plus 4x plus 1 equals 0. And that means 2x squared plus 4x plus 1 equals 0. Multiplying by negative 1 doesn't change anything. And we can find those x values using the quadratic formula. We have negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. B is 4, so b squared is 16. Then we have 4 times a times c, so that's 2 times 1. All divided by 2 times a, that's 2 times 2, which is 4. This is 16 minus 8, which is 8. And the square root of 8 can be simplified. That is the square root of 4, which is 2, times the square root of 2, which can't be simplified. And then we can divide each of those numbers by 2 if we want to. So we'll have negative 2 plus or minus square root of 2, all divided by 2. And so we get two values of x. So x equals negative 2 plus root 2 divided by 2 is one of our roots. And then x equals negative 2 minus the square root of 2 divided by 2 is the other one of our roots. So this is sort of negative 1 plus that square root of 2 over 2, which is about 0.7. This is about negative 0.3. And this is negative 1 minus square root of 2 over 2. So it's about negative 1.7. So at those two x values, f prime is 0. And I don't know what this parabola looks like, but I know that since we're multiplying it by negative 1, that coefficient is going to be a negative 2, and it's going to be a parabola that's upside down. So when I see that this function has zeros at negative 0.3 and negative 0.7, I know that the graph looks roughly like this. At negative 0.3, that numerator is 0. At negative 1.7, that numerator is 0, approximately. And since this parabola has a negative 2 as its leading coefficient, it's going to look roughly like this. So f prime is going to change signs when this function changes signs. And we're also interested in what happens to that x plus 2, because we're always to the right of x equals negative 2, right? So we can use this graph and that asymptote to infer when f prime is positive, negative, or 0. So I'm going from -2 to -1.7 to -0.3. I say f prime is this number divided by x plus 2. Well, if x is greater than -2, and this is going to be positive. So the sign of f prime is actually determined by the sign of that y value in the numerator. And that's the y value on the graph of this parabola. So between -2 and -0.7, we see the y values are going to be negative. So we'll get a negative number there for our f prime. From -1.7 to -0.3, our y values are positive. And then from 0.3 to infinity, the y values are negative. So our function goes from decreasing to increasing to decreasing at those x values, and the exact values are these, right? And the derivative is 0 at those x values. The function goes from decreasing to having a 0 slope to increasing, and then the function goes from increasing to having a 0 slope to decreasing. So f prime, or f, the original graph of f, has a relative minimum at this x value, which was that -2 minus √2/2. And it has a relative maximum at this x value. So that's -2 plus √2 divided by 2. Just using the first derivative test. So we can evaluate the original function there at those points and simplify to find the corresponding y values. And then, of course, we could take the second derivative as well. But all we were asked to do was compute f prime and find the equation of the tangent line at x naught. So let's do that. We've already computed f prime. We have inferred some relative extrema using the first derivative test. Let's just use this information to graph the function. We'll graph the tangent line, and then if we feel like it, we'll graph the second derivative. We think that's going to be insightful. This is my f of x. There's the graph. Let's graph x equals -2. That should be our vertical tangent line. And I'm just interested in, let's say, the interval from x equals -2.2 to infinity in general, but it looks like all the interesting things are happening near on this interval from -2 to say, let's say 10. Actually, let's just say 5. So it's going to look roughly like that on this interval. And then we computed f prime. When we computed f prime, we got -2x minus 1 divided by x plus 2. And we said that that function has a slant asymptote. I'm going to make that purple for my derivative. That one has a slant asymptote, y equals -2x. So the derivative is always a little bit less than that. And we're actually only interested in the x values on the domain. So we only want this for x greater than 2, or greater than -2. All right. So with all of that in mind, the claim is that when we set the derivative equal to 0, we get two values for x. The first one was x1 equals -2 minus the square root of 2, all divided by 2. So get that -1.707, which is what I got when I estimated it on paper. Let's evaluate f at that point. Actually, I really love graphing because they've defined f in more than one place. That's for a different problem. We'll just call that y for right now. So there is that minimum value. And that seems accurate because if we look at the derivative at that point, I bet we get 0. See, we see that the derivative is 0 there, so that's good. And the derivative goes from negative to positive. So the original function goes from decreasing to increasing there. So we do have a relative min, that's good. And then the other x value, we'll call that x sub 2, looks the same, but instead of subtracting that square root, we add it. Oops, that should be x sub 2. So we can evaluate f at x sub 2 rather than x sub 1 now. And we see we have a relative max there. So the function goes from increasing to having a 0 slope and then to decreasing there. We can also see that f prime changes signs. So if we get rid of those first 2 points, we see that the derivative goes from positive to 0 to negative. So the original function goes from increasing to having a 0 slope to decreasing at that x value. And the exact one is involving that square root. Now we were asked to graph a tangent line at x naught and then graph f and the tangent line on the same grid. So on this particular grid. So we're going to let y equals, this is the graph of, or the equation of the tangent line. So we'll have y equal f of x naught plus f prime at x naught. We're going to add a slider and we'll subtract x minus x naught here. And I want that tangent line just to be, let's just say it's white for right now. And make sure we plot the point x naught, f of x naught as well. Maybe I'll plot that relative maximum and the relative minimum there. Okay, and now let's just let x naught change. Let's go from -2 to 5 again. Make sure we're always going the positive direction. And try to make it relatively slow so that we can actually see what it does. So we go from negative infinity, or from -2, where the slope is very large and negative. And then at that minimum, the slope is 0. And then the slope starts to increase. And the slope has a maximum somewhere in there at a point of inflection. And then the slope starts to decrease. Well, this, yeah, the slope is decreasing. So from some maximum value to 0 again. And then the slope gets increasingly negative, and it gets steeper and steeper and steeper as we go to negative infinity. But we see we've got a 0 slope there and there, and all the tangent lines are sloping down on this first interval, so the derivative is negative. And then on the interval from this point to this point, all of our tangent lines have positive slopes, so the derivative is positive. And then when we go from there to there, all of our tangent lines have a negative slope, so the derivative values are negative. And it's relatively easy to see if we plot those points where the derivative is negative, or sorry, where the derivative is 0, there and there. And then the maximum value of the derivative is going to correspond to a point of inflection, because the derivative is going from increasing on this interval from -2 to that point to decreasing on that interval from that x value all the way to infinity. So the graph is going to go from concave upward, where the derivative is increasing, to concave downward, where the function is decreasing. Now, we weren't asked about the second derivative in this problem, but we can compute it relatively easily. We can also just let that tangent line be graphed the entire time. And if you want to, you can also plot the point that represents the slope. I sometimes like to see what the slope is of that line. So at that x value, x is 1.121, the slope is negative 2.562. And so we can see what that slope is for all the different x's. And we can see how that slope changes. We can see it graphically, and then we can also see it numerically as we look at the function values of the derivative. Okay, now for our second derivative, we're just taking the derivative of the first derivative. Now the first derivative in unsimplified form is this. So I think I'd like to just take the derivative of that. So we're taking the derivative with respect to x of that expression. And that's relatively easy to do. The derivative of negative 2 times x is just the negative 2. And this expression we can rewrite as x plus 2, to the negative 1 power. When it's written as x plus 2 to the negative 1 power, it's easier to see how to use the chain rule. We've got an inside function of x plus 2, and the outside function is that power function, raising something to the negative 1. So we're going to get negative 1 times this negative 1 coefficient is going to be a positive 1, times the inside function raised to the negative 1 minus 1, that's negative 2, times the derivative of the inside. The derivative of x plus 2 is just a 1. So our second derivative is negative 2 plus 1 divided by x plus 2 squared. And I prefer it that way when I'm thinking about limits and graphing. So this is our second derivative. And again, we're only interested in it on the interval where the function is well defined on the domain. So we're only interested in it for x greater than negative 2. Now this shows that the second derivative is positive until we get to this negative 1.29289. So that second derivative is 0 there at that x value, and then it's negative there. So the graph is concave upward until we get to this x value, and then concave downward on the other side. And I think if we get rid of that and we just focus on that teal graph, we see that it is concave upward, and then it switches to concave downward at some point. In order to find that x value exactly, rather than using the decimal approximation, we can just do the algebra on paper. We've got f double prime as negative 2 plus 1 divided by x plus 2 quantity squared. Let's do that on paper. All right, so I did a whole bunch of calculations, I think, without recording. I forgot to. I got my paper out and then I started differentiating. So we said that f double prime was this negative 2 plus 1 divided by x plus 2 squared. In order to find possible points of inflection, we set that equal to 0 and solve for x. So we've got this fraction equals positive 2. Clear the denominator, so we get 1 equals 2 times that x plus 2 squared. Then we divide by 2 and then take the square root of both sides. Don't forget the plus or minus on the side with the number. And we get x plus 2 on the right is equal to plus or minus 1 divided by the square root of 2. Sorry about the glare. And then after we have this expression right here, we can subtract 2 from both sides. If we multiply by root 2 over 2, we get negative 2 plus or minus square root of 2 over 2. Now again, remember, we're only interested in those x values in the domain. When we subtract root 2 over 2 from negative 2, we're going to be to the left of that asymptote, the one that we've already graphed. So this one, this x equals negative 4 minus the square root of 2 over 2. That's what we get when we get a common denominator there. That's not in the domain of the function. But then the other one where we're adding that square root of 2 over 2, that is in the domain of the function. So then we said the second derivative is 0 at that x value. And we're interested in when the second derivative changes sign. So we multiply by x plus 2 squared divided by x plus 2 squared to get a common denominator. Then we add the numerators, keep that common denominator. and we say, okay, that denominator is always positive. So the sign of f double prime is determined by the numerator. So I look at that numerator and I say, well, what does that look like? Well, it's just going to be an upside down parabola with a vertex at -2, 1. So it looks like this. And then we say, okay, it has roots at that -2 minus the square root of 2 divided by 2 and -2 plus the square root of 2 divided by 2. But the only one of interest to us is the one to the right of that -2. So you say, okay, well, what is the sign of that parabola, or what are the sign of the y values on that parabola when x is between -2 and -1.3? Well, we see it's positive on that interval, and then to the right of -1.3, it's negative. So f double prime goes from positive to negative at that point. So the graph should go from concave upward to concave downward. And I think that's what we see when we look at the graph. So let's graph that point. We'll graph this x value and the corresponding y value. And then we'll evaluate both the first and second derivative at that location as well. And we'll see how the extrema of f prime are related to f double prime, and how f double prime and f prime are related to f. So that's our graph. Now I don't want to graph that x naught and f prime, f at x naught, or f and f prime at x naught right now. I think I want to look at f double prime. I'm going to graph that. And then I want to graph my function at x sub 3, which is that root of f double prime. So that was -2 plus the square root of 2 divided by 2. Now we could get a common denominator, but I like writing it this way in for this particular example, because it shows us that this x value is to the right of x equals -2. So if we evaluate f at x3, this is what we get. That should be a point of inflection of the original function. So the graph goes from concave up to the left of that point to concave down to the right of that point. Now, if we evaluate the first derivative at that x value, we see that that first derivative has a relative maximum there. So the function went from, or the first derivative goes from increasing, having a 0 slope, to decreasing there. So when the first derivative is increasing, the original function's graph is concave upward. When the first derivative is decreasing, the original function's graph is concave downward. And we can see how that relates to the second derivative if we plot that point. I think I want to plot that in green. So here we see that the second derivative is 0 at that location, and the second derivative is positive there, and from -2 to that x value. So the original function is has concave upward, the first derivative is increasing, and the second derivative is positive. Now, when the second derivative is negative, the first derivative is decreasing, and the original function is concave downward. So that's kind of cool. All right. So I think that's probably enough for this particular function. We could do another example in this video, but I think I'll stop here. I like this example. I think we've done enough with it. I think the video is long enough anyway. So that's our example. It's just another example of an interesting function that involves a logarithm. We computed the derivative and we found the equation of the tangent line at x naught. We let x naught vary so that we could graph that tangent line at all of the x values in our domain. And I just let x go back and forth. Whoops, that was the one for the asymptote, sorry. We computed the first derivative to get a sense of the slope. That first derivative had a slant asymptote. That's y equals the equation of that line there, that -2x. This term goes to 0 as x goes to infinity. So the slant asymptote comes from taking the limit as this goes to infinity and then saying this goes to 0. What's the sort of dominant part? It's that y equals -2x, that line. And that's our slant asymptote. We found the zeros of x prime. and the corresponding relative extrema of the function. And then we found the, or I said f prime, excuse me. And then we found the zeros of f double prime. There was only one of those, and then we discussed when the function went from concave upward to downward. So I thought that was kind of a cool example. All right. I'll probably change the problem statement a little before I post this online for you guys. We'll do another example with a different function in the next video. Well, I like to do this with functions that have interesting graphs. Let me know if you have any questions about this.